Today we're going to look at velocity time graphs. The first thing we're going to look at is our motionless stationary ball. So let's take a look at that. And that was when we took Janet and let's say we left her at the origin and she didn't move and she just stayed at 0. So this time we're going to plot time just like we have been on the x, and velocity is going to go on the y, and this is 0 time and this is 0 velocity. And if I look at Janice and she's stationary at the origin, no matter what time I'm looking at, she's always stationary. So what is her velocity? Well, she's not moving, so her velocity is 0. So it's 0, 0, 0, 0, 0. So we just need to draw a line right along the bottom here. And that would just continue on as 0 because she's not moving. So it's always 0. Which makes sense because the ball has 0 velocity. Let me move this a little bit. There we go. Okay. So what happens when we move into uniform motion, and that would be our smoothly moving ball, right? So we have uniform motion. So with our smoothly moving ball, if we took Janet and we are going to have her at 50 centimeters at rest, but then I give her a nice little smooth push. So let's write that down. So we're going to have Janice at 50 centimeters at rest and give her a nice push. So if we do that, then we can plot our time velocity graph. So before we do that, let's draw the position time graph where we have t on the x-axis and x on the y. And remember that when Janice is starting from 50 centimeters, that's where we're going to plot her over here for our position time graph. So if I plot that, we know that it's uniform, it's constant motion, and so it looks a little something like this. And remember that that slope has to equal the velocity. So we're about to plot we're about to draw a graph of the velocity, and we know that the velocity has to equal the slope of this graph. Okay, so there's something else that we can also find from this graph, and that is the change in x. So if I were to take this over and bring this down, and then this right here is the change in x. X minus x naught. Okay. And we can find that geometrically from this graph. So let's draw the velocity time graph right underneath. Let me make my line a little straighter. I should probably use a ruler, but I'm just not that kind of person. You might need to use one at home, but it's not really my thing. So here again we have time and velocity. We are going to draw in our velocity, and it's constant. So it starts at some velocity, we'll say here, and then all along the way, no matter what time we're at. It stays at that constant velocity because we're talking about uniform motion. So it looks a little something like this. Well, this entire spot here is, of course, the change in time. And we can find something about the area under this curve. The area under this curve is actually equal to the change in x. So if we were to find this area, that would equal the change in x. So the area, let me move that over a little bit, under this curve is equal to the change in x. So you could always use that. So what is this saying? So this is your velocity, and this is the change in time. So that is saying that the change in x is equal to velocity times the change in time. And sure enough, that is the definition of average velocity. So we could rearrange that equation and solve for average velocity, and that gives us a lot to go by.